Okay, so in this video, we are talking about the derivation of Van der Waals equation of state to solve for the A and B values that are given, and talking about the compressibility factor. So this is Van der Waals equation of state, um, and this is a more accurate version of predicting how gases behave better than the ideal gas law. So if we look at a graph of more like critical temperatures, critical pressures, and critical volumes, um, it usually looks something like this. And if we want to get one certain point on that graph, we would use Van der Waals equation of state. But you need to pass in certain A and B values for whatever gas you are using, and we can easily solve for that. So if we start off by taking the equation and we derive it, so the first derivative of the critical pressure would be negative RTC, and then over VC minus B squared, and then it would be plus 2A over VC cubed. And then if we want to take the second derivative, so the second derivative of the critical pressure, it would be RTC, or it would be 2 RTC, and then over VC minus B cubed, and then minus, that would be 6A all over VC to the fourth. And then since we are trying to get those points, what we're actually going to do next is we want to multiply the first derivative by the reciprocal of the second derivative. So if we did that, well, actually, before we do that, we'll set them equal to each other. So negative RTC over VC minus B and then squared equals, actually we'll do it from the other side, so then they both stay positive. So then equals 2A over VC cubed, and then this side becomes 2RTC over VC minus B cubed equals 6A over VC to the fourth. So then if we multiply the first derivative by the reciprocal of the second derivative, then what we would get, so we get RTC times VC minus B cubed over 2RTC. Well, actually, what we can do here is, instead of doing this, we can get rid of the 2 and the 6 and just make this 3, and then that becomes 1 if we divide by 2 on both sides. So then it just becomes RTC over, or times VC minus B squared. So then that will cancel out. The RTCs will cancel out. And with this side, we are just left with the VC minus B on top. And then that will be equal to, so 2A VC to the fourth over 3A VC to the third. And then those will cancel out. These A's right here will cancel out. So then we'll be left with VC minus B is equal to 2/3 VC. And then what we can actually get is B will be equal to, so we divide by that, that's done. So then we can get B is equal to VC over 3 after canceling everything out. And then, so then we just solved for B right there without any initial given value. So we'll plug these in later. But now if we go back in, we can plug B into the first derivative to solve for A. So then if we do that, zoom out here. So then we can do negative RTC, do RTC over VC minus VC cubed, and then that squared equals 2A over VC cubed. It's still going to be squared. So then if we square that, then it becomes RTC over 4/9 VC squared is equal to 2A over VC cubed. And then from here, we can actually solve for A. So if we take this side and then put it over there, so then RTC equals 2A times 4/9 VC squared over VC. And then, so we'll rewrite it down here. I did this completely wrong. Started on the opposite side. Because we want to get rid of the A. So then if we do this, so we'll come down here. So then RTC times VC cubed over 4/9 VC squared equals 2A. So then these will cancel out right here. So then we'll be left with just RTC VC over 4/9, which we can write, which we can rewrite to, because divided by 4/9 is the same thing as multiplying by 9/4, and then equals 2A. So then if we divide again, then this just becomes 9/8 RTC VC equals A. So now we solve for our A parameter, and we can go ahead and plug that back in to the original equation, and let's do that real quick. So we get, so PC equals RTC over VC minus, and then our B was VC over 3. So again, this just becomes 2/3 VC minus our A value, so 9/8 RTC VC all over VC all over VC squared. So then if we want to compress this down, then realistically what we're going to do, so we can cancel those right there. Yeah, so we can go ahead and factor out RTC over VC, and that will leave us with a 3/2, because this will go back up to the top. You have to, because it's 1 over 2/3, so that just becomes 3 over 2 minus our 9/8. So then when we're done with that, so this is all equal to PC. So then after that, we have PC equals RTC over VC times, and this just is 3/8 after that's all done. Oh, that's not 8. 3/8. So now we have this, and this is our compressibility factor, and essentially, well, actually, no, it's not yet, because if we do this, we can rewrite it as 3/8 is equal to PC VC over RTC. So this is what we have, and we just label this as a Z for the compressibility factor. And what we can do from here is, so we got here without any sort of information about whatever gas we're dealing with at all. So the way to get our A and B values back into the equation and find whatever we need out of the certain gas. So like so we can write, if we want to try to find the critical volume, and we are given the critical temperature and critical pressure, which most of the time we know because critical volume is a lot harder to find than the critical temperature and pressure, we can go ahead and rewrite this and solve for it again. So then if we want to find VC, so that's just going to, there we go. VC will be equal to our 3/8 RTC over PC. And then if we look back up here with our B value, now that we solved for VC, we can just plug that in and find our actual B value. And so if we do that, we can just say our B is equal to 3/8 RTC over PC, and then that was over 3 if we look back above. And then what we can actually do is, so these 3's cancel out, so this is just going to be equal to RTC over 8 PC. So there, I mean, we just found our B parameter of back up here if we know just the critical temperature and critical pressure of a gas, because we're trying to get to the critical volume. And we could do the same thing for A. So we can say, so our A was equal to 9/8 RTC VC. So if we do that, 9/8 RTC, and then pass in the VC, so 3/8 RTC PC. And then after that, we can take this, so it's multiplied. So then this becomes 27 over 64, and then these go over, so then that's just R squared TC squared, and then this is over PC, and this is equal to our A parameter of that value without knowing the critical volume. And so from here we can just use these A and B parameters to solve using the van der Waals equation of state without known given critical volumes, because those are a lot harder to find experimentally than the critical temperature and pressures are.